Section 4. Charles's Law and Hot Air Balloons. Chem Talk. Charles' Law. Charles' experiment was similar to Boyle's. In France, in the early 1800s, there were many advances made in the understanding of gases and their behavior. Hot air balloons were becoming popular at that time, and scientists were challenged to improve the performance of these balloons. A French scientist, Jacques Charles, made many observations and measurements on how the volume of gas was affected by changes in temperature. Charles discovered that a quantity of gas kept at a constant pressure expands as it warms and contracts as it cools. The equipment used by Charles was very similar to that employed by Boyle. A quantity of gas was trapped in a glass tube that was sealed at one end. This tube was immersed in a water bath. By changing the temperature of the water, Charles was able to observe the change in volume of the gas. The pressure was held constant by adjusting the height of mercury so that the two columns of mercury had equal height, and so the pressure was always equal to the atmospheric pressure. This allowed Charles to examine the effect of only one variable, temperature, on the volume of gas. Through repeated experimentation with many different gases, Charles found that there was a relationship between the volume of a gas and the temperature of a gas. Your class's graph from the investigation demonstrated that direct relationship. Relationship between the temperature and the volume of a gas. Charles's law states the volume of a gas varies directly with the temperature, measured in kelvins, for a given amount of gas at a constant pressure. And the equation is volume equals a constant times temperature. And then another formula is volume divided by temperature equals a constant. Expressed mathematically, volume equals, or where K is a constant. You can compare the volumes of the same gas at two different temperatures. Kinetic theory of matter and Charles's law. A mass weighing 10 newtons, approximately 2 pounds, is supported by a column of air in a piston. The air must be supplying a force of 10 newtons to keep the mass from falling down. When the air is heated to a higher temperature, the mass rises due to the increase in volume of the air. The piston stops moving when once again the air is supplying a force of 10 newtons to keep the mass from falling. The kinetic theory of matter provides a way to understand this relationship between the temperature and the volume of a gas at the nanoscopic or molecular level. The particles of a gas are moving about with a range of speeds and corresponding kinetic energy. These particles can collide with the walls and the movable piston. These collisions create the pressure, or force per area, on the piston. The particles hit the piston so that the average force on the piston is 10 newtons. When you increase the temperature of the air, you are increasing the speed and kinetic energy of the air molecules. These molecules hit the piston more often and with a greater force. If the average increased force is 12 newtons, then the mass will move up. When the piston moves up, it increases the volume. As the volume increases, these energetic air particles don't hit the piston as often because of the extra distance they must travel. The average force of the energetic particles once again becomes 10 newtons, and the piston remains in its elevated position. When the air cools, the particles have a decrease in their kinetic energies. They hit the piston less often, and the average force is now less than 10 newtons, and the mass descends again. Absolute zero and the Kelvin temperature scale. If a decrease in temperature results in a decrease in volume, what happens if the temperature is lowered to a point where the volume drops to zero? A negative volume is impossible, so the temperature at which the volume drops to zero must be the lowest temperature that can be achieved. This temperature is called absolute zero. Absolute zero is the lowest possible temperature. It is 0 degrees Kelvin or negative 273 degrees Celsius. Whenever determining the effect of a temperature change on the volume of a gas, you must first convert from the Celsius temperature to the Kelvin temperature. You do this by adding 273 to the Celsius temperature. Kelvin equals the given Celsius temperature plus 273. So you can take any measurement in degrees Celsius, you add 273, and then that equals Kelvin. Kelvin equals degrees Celsius plus 273. Applying Charles' law. The mass of your plastic hot air balloon is the mass of the plastic plus the mass of the air. To get the balloon to fly, you have to decrease the mass of the air in the balloon. In the hot air balloon investigation that you conducted, you found that the hot air takes up more volume than the cool air. Filling your plastic balloon required less hot air than cool air. With less air in the balloon had a smaller total mass and it could fly. Example: a balloon is in a room at 25 degrees Celsius. The volume of the balloon is 2 liters. Suppose that the balloon is taken outside at a temperature of negative 5 degrees Celsius. What will be the new volume of the balloon? Charles' law lets you predict what the volume of the balloon will be. All right, you take the volume 1 divided by temperature 1 equals volume 2 divided by temperature 2. So let's plug these in here. You have a volume of 2 liters. Okay, that would go up here, V1. Your T1, your temperature 1, that would go, you just plug them in. V1, V1, T1, T1, you just plug those numbers in. And then there's your negative 5 degrees Celsius. There's your T2, so you'd plug that in there. So it's asking what is V2. Notice that temperature in Kelvin must be used to solve problems with Charles' law. Okay, so we're going to have to convert, you would have to convert the degrees centigrade to Kelvin, which they did here. They took negative 5 plus 273, and that's how they got the 268 Kelvin. Looking back up at this formula, they just took that plus 273 to get the Kelvin. So that's why they took negative 5 plus 273. That's how they got that. Notice that temperature in Kelvin must be used to solve problems with Charles' law. Rearrange Charles' law equation to solve for V2. Okay, so you're plugging these in again. So V1, so volume 1 times temperature 2 divided by temperature 1. Okay, the numbers are up above, so we just drop those numbers down. And then when you divide that, you get 1.8 liters. So volume 2 equals 1.8 liters.